Hey everyone, have you ever run into a project where you need to reverse engineer something with dual curves, like the backside of this wireless phone? One of our viewers actually came across this same dual curve challenge and he sent me his scan so I could show you how to reverse engineer it in CAD. This scan was captured with the Creality Raptor Pro and shared with me in point cloud format. So in this video, I walk you through how to model a dual curve object in CAD. You will run into geometry like this pretty often, especially when working with automotive parts. Most professional CAD programs can handle dual curved surfaces, but since the object we are working on has a thin shell, the best way to model it is with the loft command. That means the CAD software needs to support lofting with curved rail. Lofting along the length of an object is pretty straightforward. The real challenge is figuring out how to finish the profile smoothly at the end. When you reach the end of the profiles where the dual curved surface starts to form, you need to fan out your 2D sketches like this and build several lob sections. That way, the transition stays smooth. In this tutorial, I'll be reverse engineering the model using BricsCAD. I have included a download link for the point cloud file in the description so you can follow along step by step. The first step before modeling is to align the object. Since this is a symmetrical part, I will only model one half, but it is important to align the model exactly at the center of the mirror plane. I'm using the alignment function to snap the straight side of the point cloud to a horizontal line, and I'm doing that with two reference points. Now the point cloud is perfectly aligned horizontally with zero deviation. Next, I draw a line, use its midpoint as the center, and move the point cloud to the origin. This is the most accurate way to align 3D scan data inside CAD. Next, I will create the first cross-sectional sketch profile. I set up a mirror line, rotate the UCS along the y-axis to define the sketch plane, and move the origin to the cropped point cloud. I'm using the flatten command to project the mirror axis onto the new sketch plane. I'm tracing the point cloud with arcs. Avoid using splines for 2D sketches, they can cause issues later. Now I'll join all the segmented arcs together, then offset the profile by 1 mm to define the shell thickness. Next, I close the profile by rejoining all the lines into a single continuous sketch. I'm now creating the second sketch profile following the same workflow as the first. Remember, you need at least 2 sketches to run the rough command. Now I'm creating the guide rails. The first 2 are simple straight lines, and the rest of the guide rails will be created with the splines. First, I will set the UCS to the Z-axis and snap between 2 points across the sketch profiles. That creates a polar guide, letting me quickly draw a straight spline with 2 control points. Then I will fine-tune the control points by moving them along the X or Y axis using polar tracking as the guide, red for X and green for Y. These 2 rails sit on the mirror plane. They must remain perfectly straight on that plane, but they can curve vertically. At this stage, guide rails are needed on both the outer and inner wall. The loft command consumes the sketch profiles, so you will need to copy them for later use. Executing the loft command is straightforward. Select the sketch profiles first, then click on the guide rails. Here is the first loft section. You can see the surfaces align perfectly with the point cloud. Next, I'm creating a fan-out cross-section at the corner. I'll start with a pivot line on the previous cross-section, then add another line at a 45-degree angle. Then I will create a new sketch plane using the 3-point UCS. I'm creating the sketch profile in the same way as the previous cross-section. Notice how the point cloud from the Creality Raptor is very thin and noise-free, which makes tracing faster and easier. You can also rotate the Z-axis so the spline control point adjustments align normal to the surface. After working on a few projects in BricsCAD, I found spline adjustments are easier than in Autodesk Inventor. Next, I create the second cross-section. This one fans out from the previous section and makes a 90-degree turn. With this approach, you can change the loft direction and create smooth transitions in almost any geometry. It's a bit easier in BricsCAD because you can create sketch planes so quickly. Next, I'm creating the new loft section. This one runs perpendicular to the previous section and must connect seamlessly to it. I'm creating the sketch profile on the mirror plane, tracing the point cloud just like the other cross sections. Now I'm extracting the edges from the previous loft section to use as guide rails for the new one. By doing this, the new loft solid will join perfectly with the other section when you run the union command, giving you a very healthy solid model. And here's how you can create a dual curved shell using only the loft command. I have drawn a horizontal line here. You can see the slight taper on the right side, and I place the next cross section where the taper ends. This section has only a slight change in shape, so it can be modeled as a longer segment. Working with the Creality Raptor highlights how precision in scan data directly impacts the reverse engineering process. Unlike scans from RiverPoint, Metro Y, or Inspire 2, the Raptor delivers cleaner, more accurate point clouds. This makes sketch tracing smoother and eliminates the small mismatch that often appear when mirroring geometry. The result is perfectly symmetrical model, saving time and ensuring professional grade accuracy. I'm adding thickness to this section of the profile because I will imprint a rectangle over the top. This section doesn't change in profile shape along its length, so I will simply extrude it until it reaches the corner. I'm creating fan-out loft sections similar to the other end. One thing to note in BricsCAD, guide rails can only be lines, arcs or splines, not polylines. So when you extract an edge from the solid, you will need to convert the polylines into a spline first using the edit spline command. Next, I will select all the solid entities and run the union command. Then I use 3D mirror command to create the other half of the model. Then I will union both sides together. Next, I will create a sketch profile to cut out the battery cover. Next, I will cut out the mating face with a rectangular profile so the faces are level and flat. Next, I'll make another cutout here for the volume button. Next, I will extrude a round hollow rectangle which will be used to imprint onto the cover. I simply use the subtract command. Next, I will create small rectangle profile for the overlap lips along the cover edges. I will model this using the sweep command with rails extracted directly from the solid edges. Here's the finished CAD model. I will export the model in step 5 format and then we will check it out in the ray tracing scene. Okay, the CAD file size is only 0.8 MB, but when converted to mesh for 3D printing or rendering, it jumps to 130 MB. That's why CAD is the most valuable form of 3D model. It has infinite resolution, unlike polygon or mesh modeling. And remember this, there is no such a thing as dedicated reverse engineering software. It simply doesn't exist. Whatever object was originally modeled in CAD can be reversed in CAD. Thanks you guys for watching. I'll see you in the next video.